So question number 10. So they have give an example for a relation which is. So they are asking us to give an example. It is a symmetric but neither reflexive nor transitive. So we have to give a relation which is symmetric but neither reflexive or not transitive. So let me take a small example, that is as we have taken before, A is equal to 1, 2 and 3. So we have taken A is equal to 1, 2, 3 and the relation is, so we will take a relation as 2, 3 and 3, 2. So we are taking a relation as 2, 3 and 3, 2. This we have to prove that it is a symmetric but neither reflexive nor transitive. So we can see, by seeing only we can take this is an symmetric, but we have to write it how we should show that how it is symmetric nor reflexive or transitive. So first we will prove for the reflexive. So reflexive is, first we will write that here. So if A comma A belongs to R for every A belongs to R. So here A comma A should belongs to R, means 1 comma 1, 2 comma 2, 3 comma 3 should belongs to R. So here 1 comma 1 does not belongs to R, that is A comma A does not belongs to R. So therefore R is not a reflexive. So A is not a reflexive. Now next we have to check for the symmetric. So if, so we will write the condition, if AB belongs to R, then BA also should belongs to R. So AB belongs to R, then BA also should belongs to R. So here we have, that is 2 comma 3. So 2 comma 3 is belonging to R, and even 3 comma 2 is also belonging to R, that is A is 2 and B is 3. If we replace B, 3, 2 is also belonging to R, therefore R is a symmetric. So we have proved that R is a symmetric. Next we have to prove for the transitive. So first we'll write the condition, if AB belongs to R and BC belongs to R, then A comma C should also belongs to R. But here we know that 2 comma 3 is there. So 2 comma 3 belongs to R and 3 comma 2 belongs to R. So here we have 2 comma 3 and 3 comma 2. Means if, what is this? 2 comma 2 also should belongs to R. Means A is 2 and C is also 2. But 2 comma 2 does not belongs to R. Therefore R is not a transitive. So second one is, we have to check it is a transitive but neither reflexive nor symmetric. So we have to take an example which is transitive but neither reflexive or not symmetric. So if we are taking same thing A 1, 2, 3, then we will take one relation R is equal to 1, 2, 2, 3 and 1, 3. So we have to check for the transitive. It is transitive and it is not reflexive or symmetric. So first is the reflexive. So reflexive, here you can see here 1, 1 does not belongs to R. That is A comma A does not belongs to R. So therefore R is not a reflexive. So here doublets are not there. 1, 1, 2, 2, 3, 3, 4, 4, 1, 1, 2, 2, 3, 3 are not there. So this is not a reflexive. The next we have to check for the symmetric. So symmetric means what we have? Symmetric should be like we have here. You can see that we have 1, 2. 1, 2 belongs to R, but 2, 1. So you have to write 1 2 means should have 2 1. 2 1 does not belongs to R. You don't have 2 1 here. So it is, so therefore R is not a symmetric. Okay, the next is a transitive. Here, here we have 1 2 belongs to R, okay, and 2 3 belongs to R, and and we have then, that is, so we have 1 2 2 3. So here have A is this, B is 2, and B is 2, 3, A is, C is 3. Then we'll have 1 comma 3 also belongs to R. So this is, we have 1 comma 3 also belongs to R. So this satisfies the transitive relation. So therefore R is an transitive. So you have to say, take such an example where it proves this condition only. So third question is, the third under the, we have to give third example is, it should be reflexive, symmetric, but not transitive. So we have to take in such an example that it should satisfy reflexive, symmetric, but not the transitive. So if we take a relation where R is equal to, where I need a reflexive, where A is equal to 1 2 3. If my set is 1 2 3, then it should satisfy reflexive, means I need the doublet for all these elements. So I'll write it as 1 1 1, sorry, 2 2 3 3. Okay, now my reflexive will satisfy. Now next I have to check for the symmetric. So symmetric, I'll take it as 1 2 and 2 1 2 1. Okay, the next I have to check for the transitive also. So I'll take 2 3 and 3 2. So this is my relation. Now I have to check for the reflexive, symmetric, and not transitive. So the first is, I'll check for the reflexive. Here 1 1 2 2 and 3 3 belongs to R. So 1 1 2 2 3 3 are belonging to R. So we know that for all the A comma A should belong. So have one A comma A for all the elements. So 1 1 2 2 3 3 I have. So therefore R is a reflex. So R is a reflexive. Next is for symmetric. Here we know AB should be there in the relation, and BA also should be there. So if we have here 1 and 2, we have 1 and 2 in the relation R, then 2 and 1 also is belonging to R. The same way, if we take 2 and 3 belongs to R, then 3 and 2 also belongs to R. Yeah, so we have 3 and 2 also belongs to R, and we have 1 1. So 1 1 is the same thing. If we take A and B, again it is the same, 1 1 only you get. So it is an R. Therefore R is a symmetric. So next we have to check for the transitive. So transitive. Here, if I am taking 1 2 and 2 3, so I am going to take this and this. That is, here 1 2 belongs to R, and 2 3 belongs to R. 1 2 and 2 3 are belongs to R. So this is my A and B, and this is my B and C. Then AC should be 1 comma 2, but 1 comma 3, my C should be 1 comma 3, where 1 comma 3, do we have 1 comma 3? No, we don't have 1 comma 3. So 1 comma 3 does not belongs to R. Therefore R is not a transitive. So the fourth one is, we have to give an example that is reflexive, transitive, but not a symmetric. So we have to take such a relation that it satisfies the reflexive, transitive, but not the symmetric. So I will be taking R is equal to, so I have to satisfy the reflexive. So for every A, there should be a doublet. So 1 comma 1, 2 comma 2 and 3 comma 3. Okay. The next I should have a transitive. Transitive means I will take 1 comma 2 and 2 comma 3 and 1 comma 3. So here we don't have a 2 comma 1 or 3 comma 2 or 3 comma 1. So this will be my relation. We will prove that whether this is reflexive, transitive, nor symmetric. So first is for reflexive. So here we have 1 comma 1, 2 comma 2 and 3 3 belongs to R. So we have the doublet. So therefore R is a reflexive. Okay. The next is the symmetric. Symmetric, here we have seen that here we have 1 comma 2 belongs to R, but 2 comma 1 does not belongs to R. So it is not a symmetric. Again, if you see, again same with 2 comma 3 belongs to R, but 3 comma 2 does not belongs to R. The same way 1 comma 3 belongs to R, but 3 comma 1 does not belongs to R. So does not belongs to R. Therefore, R is not a symmetric. R is not a symmetric. So R is not a symmetric. Next is a transitive. So here we have 1 comma 2. Yes. Then we have 2 comma 3. Then we have 1 comma 2 belongs to R and 2 comma 3 belongs to R. That is 1 comma 3 also belongs to R. Right. So therefore R is a transitive. R is a transitive. So the fifth one is it should be symmetric, transitive. The relation should be symmetric, transitive, but not the reflexive. So we'll take such an example where it satisfies the symmetric, transitive, but not the reflexive. So it is, I'll take 1 1 and 1 2 and 2 1. So first we'll check for the reflexive. So reflexive. So we will tell if a function is a reflexive. So a comma a should belongs to R for every a belongs to R. So means here a has 1, 2 and 3. So all the a should be there. Means 1, 1, 2, 2, 3, 3. So we have here we have 1 comma 1 belongs to R, but 2 comma 2 and 3 comma 3 does not belongs to R. So we have 1 comma 1, 2 comma 2 and 3 comma 3 is not there in this set. So therefore R is not the reflexive. So R is not a reflexive. For one doublet is also missing, then it is not a reflexive. Means all the elements should have the doublet. The next is we have to check for the symmetric. So in symmetric we know AB belongs to R, then BA should also belongs to R. So here if we take 1 comma 2, so here we take 1 comma 2 belongs to R, that is 2 comma 1 also belongs to R. So we have even 2 comma 1 is also there. So therefore R is a symmetric. So R is a symmetric. Next we have to check for the transitive. So in transitive we know that if A comma B belongs to R and B comma C belongs to R, then A comma C should also belongs to R. Right? So if we are here we take 1 comma 2 and 2 comma 1. So 1 comma 2 belongs to R and 2 comma 1 belongs to R. So this is my A, 1 is my A, 2 is my B, again B is my 2 is my B, and 1 is my C. So that is, we'll get 1 comma 1. So 1 comma 1 also belongs to R. So therefore R is a transitive. So you have to give us such an example that it does not satisfy the reflexive, it satisfies symmetric and transitive. Question number 11. Show that the relation R in a set A of the points in an plane given by R is equal to P comma Q such that the distance of a point P from an origin is same as the distance of the point Q from the origin is an equivalence relation. Further, show that the set of all points related to a point P not equal to 0, 0 is the circle passing through P will be the origin as the center. So here the question tells that there is a relation R in a set A, where set A is the point in a plane. So the relation is given that P is related to Q such that the distance of a point P, so we have a distance of a point P from the origin is same as the distance of the point Q from the origin. So let's take an x-axis and the y-axis. So this will be my x-axis and this is y-axis. So this is my origin 0, 0, and if we consider an point, so if we consider a point P such that, so point P, so we'll take a point P, we'll consider it has an 5 units and an point Q which is also 5 units. So they have told that the distance between P to origin and Q to origin is equal. So we are considering it has an 5 units. Both I am considering has a 5 units. With the origin, let us take this as a 0. So now we have to prove that it is an equivalence relation. So that we have to prove reflexive, symmetric and transitive. First let me solve the first part of the question. So first we have to prove for the reflexive. So reflexive, what? A relation is reflexive. If relation is reflexive, if A comma A belongs to R. So for all the values of A comma A should belongs to R. So here if I have to take that P comma O is 5 units. If I am taking the same line again twice, then the line itself equal to itself. So if I am taking P comma P, so belongs to R, that is OP is equal to OP. So it is OP is equal to OP because the same line is equal to itself only. So therefore R is a reflexive. So we have proved the reflexive. The next we have to prove for the symmetric. So a relation is symmetric. If we tell that the relation is symmetric, if A comma B belongs to R, then B comma A should also belongs to R. So here I will consider as P comma O is equal to Q comma R. So here I am taking A has P comma O and B has Q comma R. So if P comma O is equal, then Q comma is also equal to P comma O. So first we will take it as P and Q. We are going to take 2 points, that is P and Q belongs to R. That is, we know that it is OP is equal to OQ. So OP is equal to OQ because it's already given in the question that point P is equal distance from the origin to the point Q to the origin. So O comma P is equal to O comma Q. That also implements that it's nothing but OQ is also equal to OP. It's the same because this is also 5 units and this is, the QO is also a 5 units. So therefore Q comma P also belongs to R. So therefore R is a symmetric. Next we have do for transitive. We have so a relation is transitive. If we tell the relation is transitive, if A comma B belongs to R and B comma C belongs to R, then A comma C should also belongs to R. So here we have OP and QO. Now let us take another point such that here it will be point S. So you're taking O comma P, which is also a 5 units. So here we know that P comma O is 5 units is equal to Q comma O. Again Q comma O is equal to S comma O. So we'll take first as P comma Q. If P comma Q belongs to R, that is, so OP is equal to OQ. Okay, next Q comma S belongs to R, that is O OQ belongs to OS. So OQ belongs to OS because this is also 5 units and OS is also 5 units. This means that see OQ is equal to OP is equal to OQ, then OQ is equal to OS, OP is equal to OS. So we can tell that OP is also equal to OS, that is P comma Q also belongs to R. Therefore, R is a transitive. So we have proved a reflexive, symmetric and transitive. So the relation R, so relation R is an equivalence relation. So we have proved reflexive, symmetric and transitive. So all three conditions are satisfied. So the relation now it is a equivalence relation. So the next part of the question was show that the set of all points related to a point P not equal to 0, 0 is a circle passes through a point P with the origin as the center. So here P is of 5 units and Q is of 5 units and S is of 5 units. We know that PO and QO and SO are of same length. So if we take any other point other than this, like R, which is also 5 units, T is 5 units. Again, if we take U has 5 units, V has 5 units, then W has 5 units. So if we take all these points, we know that all these points are related to P because all the length from the point to the origin is of 5 units. So 5 units. So keeping this point, we can form a circle. So if we draw a circle, if we join all these points, it will form a circle. So it will form a circle. You will get a circle. So how can we write this in the wordings? We will see. So here, the question was what? P comma Q, a distance of a P from the origin is same as the distance of Q from the origin. So we know that the distance from OP to QO is same, and same way we had checked for even for OS also. So all the points that is relation with Q. So this point Q, P, whatever the P is there, all the points are related to point P because all these points will have the same distance from the origin. So we can tell that OP is equal to OQ, OQ is equal to OS, and if we take other points is also same like R, T, U, V, W, all the points will be of same 5 units only. So it is related to P and with origin has 0 comma 0 and with the radius of O comma P. So if we draw a circle, so if we draw a circle keeping origin as the center, then all these points will lie on the circumference. So this will form a circle with an O and radius has OP. So now all the points are related to P is in the circle. So this is how we have to write the solution for this question. So question number 12, show that the relation R defined in an set A of an all triangles has R is equal to T1 comma T2, where T1 is similar to T2 is an equivalence relation, and show three right angled triangles T1 will with a side T1 with the side 3, 4, 5 and T2 with the side 5, 12, 13 and T3 with the side 6, 8 and 11 which triangle among T1, T2 and T3 are related. So the first, the relation R they have given with the set A of all triangles. So all triangles means we know so many triangles, that is equivalence triangles, isosceles triangle and scalar triangles. So they have told that the T1 triangle is similar to T2 triangle. See, similar means what? They are in the ratio. So they will be in the ratio. For an example, if we take a triangle, two triangles, that is two triangles I am taking. If this triangle, the angle are in the ratio with this triangle, this angle is ratio in with this with this and this with this. Imagine if this, all the triangles are of 60 degree. So 60 degree and even this is of 60 degree. So both will be in the ratio because all the angles are of the same. So angle 1 will be what similar to angle 2, and few times you will have an angles like sides also are in the ratios, that is 1, 2 and 3, and this will be 2, 4 and 6. If we take two triangles where one angle has 1, 2, 3 has its sides and the other triangle has 2, 4 and 6, you can see this side is in the ratio with this with 1 by 2 and this one by 2 by 4, like 1 by 2 is equal to, like this is with 2 and this side is 4. So again it is in 1 by 2 and this is 3 and this will be 6. So you can see this is 1 by 2. Again this is in the ratio of 1 by 2 only. Again this is in the ratio of 1 by 2. So these triangle 1 is similar to the triangle 2. Now we have to prove that it is an equivalence relation. So we have to prove for reflexive, symmetric and transitive. So let's see for the reflexive. So reflexive, a relation is reflexive if A comma A belongs to R. So here A comma A belongs to R means the triangle is similar to itself only. So if we are taking a triangle, that is 1, 2 and 3. So we know this is my T1 triangle where it should be similar to itself. So obviously the same triangle, if you write it is same to this O itself triangle only. So we can write it as T1 comma T1 belongs to R, that is a triangle is So the triangle is similar to itself, so it will be the same. If you are taking another triangle with 1 and 2, it will have the same side, so everything will be in the ratio of 1:1 only. It will be in the ratio. So therefore R is a reflexive. So R is a reflexive. So we have proved for reflexive. The next we will check for the symmetric. So a relation is symmetric. If we tell that relation is symmetric, then A comma B belongs to R, then B comma A should also belongs to R. So here we have told that A comma B belongs to R, then B comma A also should belongs to R. So if we take in one more triangle, this is my T1, right? If I am taking in one more triangle, that is T2 triangle, it is 2, 4 and 6. So I am taking a second triangle, 2, 4 and 6 has its sides. So the first is we have to check for the relation T1 comma T2. So T1 comma T2 belongs to R. So we are telling T1 comma T2 belongs to R, where you can see those ratios, like the first angle T1 will be 1 by 2 is equal to 2 by 4 is equal to 3 by 6. You can see the sides, all the sides are in the ratio, that is nothing but is equal to 1 by 2. So all the ratios will be 1 by 2. So you know that it is in the relation. So they are similar. So that is T1 is similar to T2. That is T1 is similar to T2. Now we have to prove that T2 is similar to T1. That is, so if we are taking, we have to prove that is T2 should be similar to T1. So if we take this the same thing, like the first is 2 by 1 is equal to 4 by 2 is equal to 6 by 3. So you can see all the ratio is nothing but is equal to 2. So it is proved that, so it implements that T2 and T1 also belongs to R. So you can see that all the sides are in the ratio. So they all are in the same ratio, that is 2 you will get. Therefore, R is a symmetric. Okay, the next we have to check for the transitive. A relation is transitive. If we tell a relation is transitive, that is A comma B belongs to R and B comma C belongs to R, then A comma C should also belongs to R. So here if we take, so if we will take one more triangle, that is 3 3 triangle, so this will be my 4, 8 and 12. If you are taking another triangle T3, that is 4, 8 and 12, then we have already seen that T1 belongs to T3. That is, we have seen that T1 and T2, T1 comma T2 belongs to R, that is we have seen here are similar. So we have seen that 1 by 2 and 2 by 4 and 3 by 6 is nothing but in the ratio of 1 by 2. So therefore it is T1 is similar to T2. Okay. Now next if we are taking T2 comma T3 belongs to R. So T2 comma T3, that is nothing but, see, 2 by 4 is equal to 4 by 8 is equal to 6 by 12. That is, in everything is in the ratio of 1 by 2. So all sides are in the ratio of 1 by 2. So T2, that is T2 is similar to T3. So we have proved that T2 is similar to T3 also. Now we have to check for T1 comma T2. So we have to take, we have seen this is similar to this by with the ratio of 1 by 2, and this is T2 is similar to T3, that is also it is in the ratio of 1 by 2. Now we have to check for T1 in T2 triangle is in the ratio or not. So that is, so first we have to take, that is T1 triangle and T2 triangle. T1 and T3 we have to take, that is nothing but, so 1 by 4 is equal to 2 by 8 is equal to 3 by 12. So you can see that these all are in the ratio that is 1 by 4. They are in the form of 1 by 4 ratio. So all sides are in the ratio 1 by 4. Therefore, T1 is similar to T3 also because all are in the ratios. So therefore T1 belongs to T3. So T1 and T3 belongs to R. Therefore, R is a symmetric. So now we have proved a reflexive, symmetric and transitive. So R is a equivalence relation. So now R is a equivalence relation. We have proved R is an equivalence relation. Okay, now let's see the next part of the question. So here they have given us consider three right angled triangles, T1 with the sides of 3, 4 and 5 and T2 with the sides of 5, 12 and 13 and T3 with the sides of 6 and 8, and we have to check which is related, whether T1 is related to T2 or T2 is related to T3 or T1 is related to T3. We have to check which is related to here. So let's write. We know that they have given it as a right angle triangle. So I am going to write a right angle triangle, three right angle triangle. So here I have in three right angle triangle. This is T1, T2 and 3, 3. So we know that it is a right angle triangle. All the angles will in this angle will be 90 degree. So all the angles will be 90 degree and it will be similar. So we will consider the sides. So first T1 is 3, 4 and 5. We know in always right angle triangle the highest value will be for the hypotenuse. So if I am taking this as a 5, that is 3 and 4, and T2 in triangle I'll take hypotenuse as 13 and this will be 5 and 12, and in the T3 triangle this will be 10, 6 and 8. So now we have to check for these sides whether are in the ratio or not. So if we take first as T1, triangle T1, if you are taking a triangle T1 with T2. So I am taking with T1 and T2. So if I am taking triangle with T1 and T2, I have 3 by 4, sorry, 3 by 5. So first is 3 by 5, then 4 by 12, then I have 13 by, sorry, 5 by 13. So I have 3 by 5, 4 by 12 and 5 by 13. So 3 by 5, 4 by 12 and 5 by 13. 5 by 13. So if we see this is the ratio is 3 by 5, and what will be the ratio of this? This will be 1 time and this will be 4 times, and this is 5 by 13. You can see that all the ratios are not equal. You can see all the ratios are different. This is 3 by 5, this is 1 by 4 and this is 5 by 3. So T1 is not related to T2. Now next we will check for the T2 and T3. So T2 if taking that 5 by 6, so it is 5 by 6. Next is 12 by 8, that is 12 by 8. Then again you have 13 by 10. 13 by 10. You can see this is 5 by 6, but what will be the this ratio? This will be 2 by 4, 2 by 3, sorry. So this will be 3 by 2 and this will be 13 by 10. So all these are not equal, are not in the ratio, because 5 by 6 and you have 3 by 2 and you have the 13 by 10. So T2 is not related to T3. Now if we are taking T1 and T3, so we are taking triangle T1 and T3, that is 3 and 6. So you have 3 and 6. Again you have 4 and 8. 4 and 8. Then 5 and 10. So you have 5 and 10. So if we check, this is 1 by 2. Again 4 is also, it's also 1 by 2 in ratio. So you can see all are in 1 by 2 ratio. So T1 is all are equal. All sides are in the ratio that is 1 by 2. So T1 is related to T2. So how we are going to write this in the word form is, so we have to take that T1 has a side 3, 4 and 5, and T2 has a sides 5, 12 and 13, and T3 has a sides 6, 8 and 10. So here the two triangles should be similar. So two similar triangles, two right angle triangle, the two right angle triangles are similar if the ratio of their sides are equal. So the ratios, their sides should be equal. See, you have seen like 1 by 2, 1 by 2, it should be equal. So here for T1 comma T3 are at the ratio that is 3 by 6, 4 by 8 and 5 by 10 are in the ratio of 1 by 2. So we know that since the ratio is similar, since the ratio is same for all the sides, sides that is T1 and T3, T1 and T3 are similar. T1 is T3 are similar. That implements that T1 and T3 are related. So that is T1 is similar to T3. That is T1 and T3 are related. This is how we have to solve for the second part of the question. Thank you for watching. Please subscribe.